Have you ever found yourself, zooming effortlessly from a global satellite view all the way down to your own backyard on Google Earth?
Oh, yeah, definitely.
Or maybe typed a query into Google search and like billions of web pages scanned and returned in what feels like the blink of an eye. It's pretty astonishing, right?
It really is.
That seamless instant access to just massive amounts of data feels almost like magic sometimes.
It absolutely does. But behind that apparent magic is this incredible feat of engineering. It's like an invisible infrastructure that lets the internet function at a scale most of us can barely even imagine.
Yeah.
It's the kind of tech that quietly underpins, well, so much of our digital lives.
And today we're pulling back the curtain on one of the foundational pieces of that very infrastructure. Welcome to the Deep Dive, where we unpack complex ideas to give you the essential insights.
That's right.
Our mission today is to demystify a truly revolutionary paper, Bigtable, a distributed storage system for structured data, which Google published way back in 2006.
And look, this isn't just some old tech paper gathering dust somewhere. It's really a blueprint. It essentially laid the groundwork for how so many of the massive modern data systems we rely on today actually operate.
Wow.
Its concepts, I mean, they continue to influence everything from cloud databases to data analytics platforms, even now.
So by the end of this deep dive, you'll not only understand Bigtable's unique approach to data storage and why it was just so crucial for Google back then, but you'll also grasp the really ingenious solutions it presented for handling data at a completely unprecedented scale.
Yeah, think of it as a shortcut. You'll be really well informed about a piece of tech that, honestly, quietly changed the world.
Okay, let's dive in.
Let's do it.
So when we talk about Bigtable, we really have to start with the sheer magnitude of the problem it was trying to solve. If you can, cast your mind back to Google in the mid-2000s, what kind of data scale were they even grappling with, and why was that such a huge challenge for the storage systems they had at the time?
Well, even back in 2006, Google wasn't just big. It was operating at a scale that fundamentally broke the existing paradigms. I mean, they were talking about petabytes of data.
Petabytes?
Yeah, that's thousands of terabytes or millions of gigabytes. And this data was spread across literally thousands of commodity servers, just regular off-the-shelf machines.
Right.
Now, this wasn't just about, dumping files into a giant bucket. It was specifically about managing structured data.
Structured data, okay. What does that mean exactly in this context?
Think of data that has some inherent organization, things like web pages, user preferences, geographic imagery tiles for Google Earth, or advertising data, data with fields and relationships, basically.
Got it.
So making that amount of organized data quickly accessible, reliable, and consistent across this huge, sprawling infrastructure of interconnected, potentially unreliable machines, that was a challenge unlike anything seen before.
And I guess it wasn't a static problem either, right? The demands on this data storage system must have been incredibly diverse, not just one type of workload.
Absolutely not. And this is where it gets really interesting. Google's applications placed, as the paper says, very different demands on their storage system, often all at the same time.
Okay.
So on one end of the spectrum, you had services like, say, Google Finance. Imagine wanting a stock quote right now or up-to-the-minute financial news.
I missed it.
That demands extremely low latency, real-time data serving. Users expect near-instant responses. Milliseconds matter.
But then on the complete other end, you've got something massive like web indexing.
Exactly. Web indexing involves these huge, throughput-oriented batch processing jobs. We're talking scanning billions of web pages, extracting information, storing it for search. This isn't about single-digit millisecond responses. It's about processing vast quantities of data as quickly as possible. High throughput is the goal there.
Okay, so you have these two completely opposing needs. Super fast, low latency reads and massive high throughput batch rates.
Right. And the challenge is that these two extremes typically require completely different database designs. Traditionally, you'd optimize for one or the other.
So building one system that could gracefully handle both without, bottlenecking either one.
That was, well, nothing short of a monumental task, a huge engineering challenge.
So given these immense and incredibly varied demands, why couldn't Google just go out and, buy an off-the-shelf solution? Yeah. Surely there were the big enterprise databases available back then. What were their limitations at this kind of Google scale?
Yeah, that's a really crucial point. Traditional relational databases, things like Oracle or DB2, while they were incredibly powerful and offered a full relational data model with ACD transactions and all that.
The standard stuff.
The standard stuff, yeah. They just weren't the right fit. For one thing, they typically didn't scale out horizontally across thousands of those commodity machines in the way Google absolutely needed.
Okay.
Trying to manage petabytes of data with dynamic growth and really unpredictable access patterns on a single monolithic relational database or even a cluster of them, it would have been prohibitively expensive and just architecturally unsound.
So they were too rigid in some ways. Is that fair to say?
Precisely. A traditional relational model imposes a very strict schema. You have to define everything up front.
Right. Tables, columns, types.
Exactly. And while that's powerful, that rigidity makes it really cumbersome to evolve your data model rapidly. And that's essential when you're Google and you're constantly adding new products or features.
Constantly changing, yeah.
Bigtable needed to provide much more dynamic control over the data layout and, critically, over locality properties.
Locality, meaning where the data physically sits.
Exactly. How data is physically stored to optimize specific access patterns. Traditional databases just didn't offer that kind of control at this scale. Plus, the overhead of a full relational model with its complex query optimizers and transaction managers would have introduced unacceptable performance bottlenecks for Google's needs. They needed something fundamentally more flexible and, frankly, tailored.
Okay, that makes sense for relational databases. But what about other types? Were there parallel or in-memory databases emerging then that were pushing performance boundaries? Were they not suitable either?
True, those systems existed and had achieved impressive scalability and high performance in their own right, often for specific analytical workloads. But the key distinction here is that Bigtable provides a fundamentally different interface altogether.
Okay.
It wasn't trying to be a general-purpose relational database. It wasn't trying to be a system just for complex analytical queries. Instead, it was designed very specifically for Google's internal use cases.
Right. Tailored.
Exactly. Prioritizing massive horizontal scalability, high availability, and the ability to efficiently store and retrieve these vast amounts of semi-structured data with predictable performance, often for applications that didn't actually need complex SQL queries or multi-row transactions.
So it gave clients a simpler, more direct way to talk to the data.
A simpler, more direct, yet incredibly powerful way to interact with data at scale. Yeah.
So if we try to boil all this down, like to its absolute essence, what was the core, almost impossible sounding problem statement Bigtable was actually trying to solve?
Okay, the core problem was something like this. How do you design and build a single, incredibly flexible, high-performance, and highly available storage system that can accommodate such a vast and often conflicting range of workloads and data types? Everything from individual URLs and entire web pages to satellite imagery, user search histories, analytics events, you name it.
All in one system.
All in one system, and all while scaling reliably to petabytes across thousands of just commodity machines, and doing it with the consistent low latency and high throughput required by Google's, rapidly burgeoning services.
Wow.
It was a challenge that truly demanded a complete rethink of how you even approach distributed data management.
And that leads us straight to the urgency, doesn't it? We've established this monumental problem. But why was Bigtable needed right then? What was it about that specific moment around 2006 that made building this custom solution so absolutely paramount for Google's survival and, well, growth?
It really felt like a now or never moment for Google. In 2006, their services weren't just growing, they were absolutely exploding. In popularity, in complexity.
Right, what was launching around then?
Well, think about the landscape. Google Search was already a giant, obviously. But then you had these revolutionary services like Google Earth launching.
So amazing.
Totally. Google Finance, Orkut. Remember Orkut, one of the earliest big social networks. Personalized search, starting to tailor results just for you. Even Writely, which was an early web-based word processor that eventually became Google Docs.
Wow. Okay, so a ton of new stuff.
A ton of new stuff. And all these new applications needed to store and retrieve data, often in entirely new ways. And they needed to do it reliably, with consistent performance, and at a scale that, frankly, no one had truly cracked before.
So they weren't just looking for something marginally better than what existed. They were hitting fundamental, existential walls with the existing technology.
Exactly that. They were hitting walls on flexibility. I mean, just imagine trying to adapt a traditional, rigid database schema for something as dynamic as personalized search, where new user actions or data types could emerge constantly.
Yeah, nightmare.
It would have been an administrative and engineering nightmare. They were hitting walls on performance, too. Try to picture Google Maps zooming in and out if every single tile fetch or data lookup involved slow, inefficient queries across maybe disparate, unoptimized data stores.
Unusable.
The user experience would be totally unusable. And crucially, they were hitting walls on the ability to really reason about data locality.
Right, that closeness thing again.
Yeah. How could you guarantee that related pieces of data, even when they're spread across thousands of machines, were stored physically close enough to each other for rapid retrieval? This was becoming a serious bottleneck for basically every ambitious new project they had.
That sounds like a total nightmare for the engineers trying to innovate. If every new feature meant you had to battle this slow, inflexible data layer, the whole pace of innovation would just grind to a halt.
Exactly.
Like you said, trying to run personalized search, if every query required these super inefficient lookups into a user's entire history,
Yeah.
the whole system would just crawl.
Precisely. The challenges weren't just, theoretical academic exercises. They were manifesting as very real, very tangible bottlenecks for the development and the future scalability of Google's core products. And this context is absolutely critical because it makes Bigtable's design choices, which, as we'll see, are pretty unconventional if you're only familiar with relational databases, seem incredibly logical.
Ah, okay.
Bigtable is really a system born out of absolute necessity. Necessity for extreme scale, and necessity dictated by very specific operational realities at Google. It wasn't built because it was just a cool research idea.
Yeah.
It was built because Google had to build something like it to continue growing and serving its users effectively.
That sets the stage perfectly. So, okay, how did they even begin to tackle this monumental problem? What was Bigtable's big conceptual breakthrough? What was the core approach or solution they eventually landed on?
Okay, the central metaphor, the kind of conceptual breakthrough that really defines Bigtable, is its description as a sparse, distributed, persistent, multidimensional sorted map.
Okay, that's a mouthful. Sparse, distributed, persistent, multidimensional sorted map. Let's break that down.
Yeah, it sounds quite academic, but let's actually unpack it because it's deceptively simple but incredibly powerful once you get it.
Please do. Sounds like something I draw on a whiteboard and then immediately regret trying to explain.
Slight chuckle. Okay, imagine it like this. Think of a giant, maybe infinitely expanding spreadsheet.
Okay, spreadsheet. I can picture that.
But here's the twist. It's not a dense, filled-out spreadsheet where every cell has something. Most of it is empty. That's the sparse part.
Ah, okay. Sparse means mostly empty. Why is that good?
It's a massive win for storage efficiency. Bigtable only needs to allocate space for the data you actually put in rather than reserving tons of space for empty cells you might never use.
Gotcha. Save space.
Right. And it's not on one computer. It's distributed across, potentially thousands of machines. It's persistent, meaning the data sticks around reliably, even if individual machines fail. GFS helps with that, as we'll see.
Okay, distributed, persistent. Makes sense.
And fundamentally, it's a map, which just means you look up values using keys, like a dictionary or hash map.
But you said multidimensional sorted map. So it's not just one key to look things up, like in a simple key value store.
Yeah.
How does that multidimensional part work?
Right, this is where its real power shines. The core lookup in Bigtable isn't just based on one key, but a triple. You need a row key, a column key, and a timestamp.
Row, column, time. Okay.
And the value you get back at that precise intersection is simply an uninterpreted string of bytes. Bigtable doesn't care what's in it. So you can kind of conceptualize the whole thing as this function. Row.string, column.string, time.in64.string.
Okay, row string, column string, time integer gives you back a string of bytes.
Exactly. This simple yet really flexible model allowed Google to represent highly varied, sort of semi-structured data in a consistent way across all these different applications.
Okay, let's break down each of those dimensions then. Starting with the row keys. What makes them special? Anything interesting there?
Yeah, definitely. Row keys are arbitrary strings, which gives clients incredible flexibility in how they want to structure their data. They're typically on the shorter side, maybe 10 to 100 bytes usually,
Wow.
but they can technically be up to 64 kilobytes.
Wow.
But what's truly crucial here is a fundamental guarantee Bigtable provides. Any read or write operation on data under a single row key is atomic.
Atomic, meaning it either all happens or none of it happens, right?
Exactly. It simplifies the reasoning for client applications immensely. It ensures that concurrent updates happening to the same row don't lead to inconsistent or corrupted states. If you're updating, say, multiple columns within a single row, you know that all those updates either succeed together or fail together as one single indivisible operation.
That's a really powerful guarantee. It must simplify concurrent programming enormously for the people building apps on top of this.
It does.
But the real ingenuity you mentioned earlier comes from how Bigtable actually organizes these rows based on the keys.
Yes, this is where it gets really interesting, and it's a core lesson for anyone designing large-scale systems. Bigtable maintains all its data in lexicographic order sorted by the row key.
Lexicographic.
Yeah.
Like dictionary order.
Exactly, like dictionary order.
Yeah.
This means that rows with similar keys, or keys that are close in that sorted order, are stored physically close together on disk. And the entire massive range of rows for a table is then dynamically partitioned into these chunks called tablets.
Tablets.
These tablets are the fundamental units of distribution and load balancing across all the different machines. Each tablet typically holds around 100 to 200 megabytes of data by default.
So hang on. If the data is sorted by row key, that implies you could be really clever about how you design your row keys to group related information together, right? Can you give us a concrete example of that smart key design?
Absolutely, and this is a total masterstroke in the design. Take the web table example from the paper, which Google used internally to store crawled web pages. Instead of just using the page's URL directly as the row key, like www.google.com/rapsindex.html.
Which seems like the obvious thing to do.
Right. Instead, they reverse the hostname components, so that URL might become a row key, like com.google.mapsindex.html.
Huh. Why reverse it?
What this brilliant, seemingly small design choice does is it groups all the pages from the same domain, like everything under google.com, into contiguous rows in the table.
Because com.google. comes before com.google.maps, which
Yeah.
comes before com.google.search or whatever.
Exactly. So when you're doing an analysis that needs to look at all the pages from a specific domain, all that data is physically clustered together in one or maybe a few adjacent tablets. This enables super efficient range scans and reads. It's like organizing your physical library not alphabetically by title, but by author. So all the books by the same author are right next to each other, allowing you to just scoop them up in one efficient motion instead of hunting all over the library.
That is genius. Such a simple trick, but with massive implications for performance, especially at scale. Okay, so that's rows and row keys. What about the column keys? You said they're grouped into something called column families. What's that about?
Correct. Column keys themselves are grouped into sets called column families. Now, these are much more than just logical groupings. They are the basic unit of access control in Bigtable.
Access control, like permissions.
Exactly. You can specify who can read or write data within a particular column family. This allows for really fine-grained security. And critically, all the data stored within a single column family is usually of the same type and is compressed together as a unit.
Okay, so grouping helps with compression too.
Definitely. Which further boosts storage efficiency and read performance. A column family itself has to be defined when the table is created as part of the schema, but once a family exists, you can use basically any column key within that family using the familiar family.qualifier syntax.
Right, like in the web table example, they had contents for the actual page content, or maybe anchor for tracking inbound link text.
Exactly. For the contents family, the qualifier might be empty or maybe just a version number, but for the anchor family, the qualifier could be something like cnnii.com, storing the actual text of an anchor link pointing from cnsi.com to the current page's row.
Okay.
The key insight here is that while the number of column families in a table is generally small and stable, maybe in the tens or perhaps hundreds at most, you can have a virtually unbounded number of column qualifiers within those families.
So few families, but potentially millions of unique columns within them.
Pretty much. This provides incredible flexibility without the overhead of having to predefine every single possible column up front, which is a really common and often cumbersome requirement in traditional relational databases.
Yeah, alter table can be painful. Okay, that covers columns and families. And the final dimension was timestamps. Why keep multiple versions of the same data, and how do they manage that without things getting huge?
Right, timestamps. So each individual cell in Bigtable, the intersection of a row and a column, can contain multiple versions of the same data, and each version is indexed by a 64-bit integer timestamp.
Okay.
These timestamps can either be assigned by Bigtable itself, representing real time down to the microsecond level, or they can be explicitly assigned by the client application if it needs more control over versioning.
And how are they stored?
Different versions are stored in decreasing timestamp order. So the most recent version is always stored first, making default reads automatically fetch the latest data.
That sounds like built-in version control. which must be incredibly useful for things like tracking changes to web pages over time, or maybe user history.
Exactly. It's perfect for those kinds of use cases.
But how do they keep all those historical versions from just piling up and consuming, infinite storage?
Yeah.
Is there cleanup?
Yeah, absolutely. Bigtable supports automatic garbage collection of old cell versions, and this is configured on a per-column family basis.
Ah, okay. Configurable.
Clients can specify rules like keep only the last N versions, for example. You might only want to keep the last 3 crawled versions of a web page. Or you could say keep only versions written in the last X days, maybe keep history for just the last week.
Gotcha.
This mechanism intelligently prunes old or unneeded data automatically, keeping storage manageable while still offering that crucial historical data access if you need it. It's a very pragmatic approach to data lifecycle management, especially at Google scale.
Okay, so the data model itself, sparse, multidimensional, sorted, versioned, is incredibly flexible and clearly optimized for scale. How do clients, like the Google apps, actually interact with this system? What does the API look like? Is it like SQL?
No, not at all like SQL. The client API provides functions for sort of basic metadata operations, things like creating and deleting tables and column families, or changing metadata like access control rights.
Standard admin stuff.
Right. For actually manipulating data, clients can write or delete values to specific cells, row, column, timestamp. They can look up individual values. Or, and this is very common, they can iterate over subsets of data in a table using a scanner abstraction.
A scanner. What can that do?
The scanner is pretty powerful. You can use it to specify ranges of rows you're interested in. Remember, the rows are sorted, so range scans are efficient. You can filter by specific column families or even individual column qualifiers. You can even apply regular expressions to column names or filter based on timestamp ranges.
Wow. Okay, so quite expressive, even without SQL.
Definitely. It's designed for both high-throughput batch operations, like a MapReduce job reading tons of data, as well as very targeted reads for serving live requests.
That sounds quite versatile for something that's fundamentally non-relational and built for high performance.
It is. Bigtable also supports single-row transactions.
Ah, we mentioned atomicity within a row before.
Right. These are crucial for those atomic read-modify-write sequences within a single row. So if you need to read a value, update it, and write it back without anyone else interfering in between, you can do that atomically for one row. This is really important for maintaining consistency for things like counters or simple state updates.
Okay, but only single row transactions, not across multiple rows like in a relational database.
Correct. It doesn't support general transactions across multiple row keys. That's a common feature in relational databases that Bigtable intentionally omits for simplicity and performance at scale. However, it does provide an interface for batching multiple writes across different row keys at the client level, allowing applications to submit many updates efficiently in one go.
And you can use cells as counters too.
Yeah, it allows cells to be used as atomic integer counters, which is super useful for common web tasks like keeping track of page views or clicks without needing complex locking.
And given its scale and role at Google, I assume it integrates seamlessly with other large-scale processing tools they were famous for, like MapReduce.
Absolutely. Bigtable was designed from the ground up to integrate tightly and seamlessly with MapReduce, which was Google's, seminal framework for doing large-scale parallel computations back then.
Right, the foundation for things like Hadoop later on.
Exactly. They built specific wrappers that allowed a Bigtable to be used directly as both an input source and an output target for MapReduce jobs. This meant Bigtable became a truly foundational layer for Google's entire data processing ecosystem. It effectively bridged the gap between raw data storage and complex analytical processing at an unprecedented scale.
Okay, so Bigtable isn't just this standalone marvel. It actually leverages other powerful existing Google infrastructure. It really is like stacking these sophisticated Lego blocks, as you said, each designed for a specific purpose to build something truly massive and robust. What are these key underlying building blocks it relies on?
That's a perfect analogy. Bigtable is definitely built on top of several other critical, battle-tested Google systems. The most foundational layer, the thing that actually stores all of Bigtable's immutable log files and data files, is the Google File System, or GFS.
GFS. Heard of that one too. Another famous Google paper.
Exactly. GFS is a distributed file system specifically designed to handle very large files spread across many, many commodity machines. It provides data durability and high availability automatically, even if individual machines fail.
So Bigtable doesn't have to worry about disks failing or making replicas itself.
Right. GFS handles that reliability layer underneath. This frees Bigtable from having to worry about those really low-level storage details, which is a massive simplification for its own design. It also means Bigtable processes often share the same physical machines with other GFS applications, letting them leverage a common shared infrastructure pool very efficiently.
Okay, so GFS handles the raw, resilient storage layer. What about the actual format of the data that Bigtable stores on GFS? Is it just dumping raw bytes?
No, it uses a specific internal format called the SS-stable file format.
Gatable, what's that stand for?
It stands for sorted string table. Think of it as an internal, persistent, ordered, and crucially immutable map stored within a file on GFS.
Immutable meaning once it's written, it never changes.
Exactly. Both the keys and the values within an SS stable are just arbitrary byte strings. And the fact that SS stables are immutable is absolutely key to Bigtable's design. It simplifies so many aspects of concurrency control, cache coherency, recovery, and data management later on.
And are they efficient to read from?
Incredibly efficient. Data inside an SS stable is stored in blocks, typically around 64 kilobytes, and each SS stable has an in-memory index that allows for lightning-fast lookups, often requiring just a single disk seek to find the right block within the file. Some SS stables, particularly for smaller, very frequently accessed data, can even be completely matched into the server's memory for even faster zero-disk I/O access.
Okay, GFS for storage, SS stables for the file format. And then there's Chubby, which you mentioned earlier is the traffic cop. Why is Chubby so vital? It sounds like more than just file storage.
Oh, Chubby is absolutely vital. It's Google's highly available and persistent distributed lock service. You can think of it as the central nervous system, or the traffic cop, or maybe the master registry for the entire Bigtable cluster.
Okay.
It's the thing that ensures order and consistency in what would otherwise be a pretty chaotic distributed environment with thousands of machines potentially doing things simultaneously.
And how does Chubby itself stay reliable?
A Chubby service itself typically consists of 5 active replicas, and it uses the Paxos consensus algorithm internally to keep those replicas consistent, even if some of them fail or get disconnected. This guarantees high availability for Chubby itself as long as a majority of replicas are running and can talk to each other. And the robustness of Chubby is absolutely paramount for Bigtable's own reliability.
So what exactly does Bigtable use Chubby for? What critical tasks does it delegate to this highly available traffic cop?
Okay, Bigtable relies on Chubby for a variety of absolutely critical functions. First, and maybe most importantly, it ensures that there is at most one active master server in the entire Bigtable cluster at any given time.
The single orchestrator we talked about.
Right. Chubby provides the locking mechanism to guarantee that. This prevents conflicting decisions and ensures a single source of truth for all the orchestration tasks. Second, Chubby stores the bootstrap location of Bigtable's data. Essentially, it tells the system how to find itself when it first starts up. It's the very first piece of information a Bigtable client or server needs to locate the cluster's own metadata.
Like the entry point.
Exactly. Third, Bigtable uses Chubby to discover new tablet servers as they come online and also to finalize tablet server deaths. If a tablet server crashes or becomes unreachable, Chubby helps a master quickly detect that failure so it can reassign the dead server's tablets and maintain overall availability.
Okay, leader election, bootstrapping, failure detection. What else?
Fourth, Chubby stores Bigtable's schema information. Things like the definitions of column families for each table. And finally, it stores access control lists, ACLs, which determine who has permission to read or write to different parts of the Bigtable, ensuring security.
Wow, that's a truly extensive list of absolutely crucial functions. It really does sound like Chubby is Bigtable's Achilles heel then. If Chubby goes down, Bigtable is in deep, deep trouble, right?
It truly is. The paper states it quite clearly. If Chubby becomes unavailable for an extended period of time, Bigtable becomes unavailable, period.
Have they measured that dependency?
Yeah, they did. And historically, the actual impact of Chubby unavailability on Bigtable's overall uptime was remarkably low, which really speaks to Chubby's own inherent robustness. But it absolutely highlights a fundamental truth in these large distributed systems.
Yeah.
You always have dependencies. And the reliability of your system is often tightly coupled to the reliability of its foundational services.
Right.
It really raises an important question for any system designer. How do you manage and mitigate the risk associated with your most critical dependencies, even those, like Chubby, that are designed for extreme availability?
That's a really good point. It shows the deeply layered nature of these massive systems, where even the foundational layers have their own dependencies. It really is
Yeah.
like a digital house of cards, but hopefully one built by master architects.
Chuckle. That's a good way to put it.
Okay, so with those foundational layers, GFS for storage, SS tables for format, Chubby for coordination now clear, let's shift our focus back to Bigtable's internal architecture itself. You mentioned earlier there are three main components that interact dynamically. What are they, and how do they actually work together to deliver that incredible scale and performance we've been talking about?
Right, the three main components are the client library, the master server, and the tablet servers.
Okay, plant library first.
Hmm.
Is that just code running in the application?
Pretty much. The client library is simply the code that applications using Bigtable link into directly. This library handles all the communication with the actual Bigtable cluster, abstracting away a lot of the complexity of distributed operations like finding the right server for your data, handling retries, and so on. It's essentially the application's direct connection point into the Bigtable universe.
Got it. And the master server. That sounds like the brain, maybe the orchestra conductor of the whole operation.
You can absolutely think of it as the orchestrator. There's only one master server active at any given time, remember, that's guaranteed by Chubby holding a unique lock.
Right.
The master is responsible for all the high-level management tasks. Things like assigning tablets to specific tablet servers, detecting when new tablet servers are added or when existing ones fail or are removed, balancing the load across all the tablet servers to ensure an even distribution of work.
Keeps everything running smoothly.
Exactly. It also performs a garbage collection of old, obsolete files in GFS, and it handles schema changes, like when an application wants to create a new table or add a new column family.
So it's managing the overall health and structure of the Bigtable cluster.
Mm-hmm.
But here's a key question. Does all the actual data flow through the master? At Google scale, that sounds like it would instantly become a massive bottleneck.
That's a critical design choice they made, and the answer is a resounding no. Client data does not flow through the master server.
Okay.
Clients communicate directly with the appropriate tablet servers for all their read and write operations. This is a really crucial aspect of its shared nothing architecture, at least in terms of the data flow path.
So the master just tells the client which server to talk to.
Basically, yes. The client asks the master, or uses cached info where a tablet lives, and then talks directly to that tablet server. Because of this design, the master is actually quite lightly loaded in practice and is definitely not a bottleneck for the actual data operations. It's kind of like an air traffic controller directing planes. It tells them which runway or gate to go to, but the planes fly directly to their destination. They don't fly through the control tower itself.
That analogy makes it perfectly clear.
Mm-hmm.
Okay, so the tablet servers are the ones really doing the heavy lifting then, the actual workers handling the data.
Exactly. The tablet servers are the workhorses, the actual data handlers. There are many of them in a cluster, typically hundreds or even thousands, and crucially, they can be dynamically added or removed to accommodate changes in workloads or machine availability.
Okay.
Each individual tablet server manages a set of tablets. The paper says anywhere from maybe 10 to about 1,000 tablets per server, depending on the size and load. These tablet servers are the ones that actually field all the incoming read and write requests for the specific tablets they are currently assigned.
And they do more than just reads and writes.
Yes. They also manage the crucial task of splitting tablets that have grown too large. This splitting process is vital for continuous dynamic scaling and load balancing as data grows or access patterns shift.
That dynamic nature sounds like it makes the system incredibly flexible. You can just sort of throw more machines at it as your data grows or your traffic spikes, and the system intelligently rebalances itself.
Precisely. This shared nothing architecture for the data serving path, combined with the master's intelligent orchestration and load balancing, is absolutely key to Bigtable's massive scalability and its resilience to failures. You add more tablet servers, the master assigns them work by distributing the tablets, and the system just gracefully adapts to ever-increasing demands, almost like a living organism.
Okay, so Bigtable manages all this data by breaking tables down into these tablets, which we now know are essentially just contiguous ranges of rows. But in a system of this immense size, how does anything, a client, the master, actually know where each of these potentially millions of tablets lives at any given moment? It must have some kind of incredibly clever, super fast internal map or directory system.
It does, and it's a very elegant three-level hierarchy. It's conceptually analogous to a B-plus tree if you're familiar with database indexing structures, and it's designed specifically for storing and retrieving tablet location information very quickly. Think of it as a giant, highly optimized, multi-level index that tells you exactly where to find any specific piece of your immense distributed spreadsheet.
Okay, walk us through these three levels. What's at the very top, like the absolute starting point for any lookup?
The first level, the very root of the entire lookup process, is actually a special file stored in Chubby. Remember our highly available traffic cop?
Right, Chubby again.
This specific Chubby file contains the fixed, reliable location of the root tablet. This root tablet location is the absolute starting point for finding any data in any Bigtable. Without knowing where the root tablet is, the system couldn't even bootstrap itself.
So Chubby points to the root tablet. What is this root tablet then? Is it special in some way? Does it hold user data?
The root tablet itself is indeed very special, but it doesn't hold user data directly. It's actually the first tablet of a special internal table called the metadata table.
Ah, a table about the tables.
Exactly. The root tablet specifically contains the locations of all the other metadata tablets in the system. It's also unique because, unlike regular data tablets, the root tablet is never split. This ensures that the location hierarchy always remains just these 3 levels deep, providing a stable entry point for all lookups.
Okay, so level 1 is Chubby pointing to the root tablet. Level 2 is the root tablet pointing to all other metadata tablets. And then level 3 must be where our actual user data locations live, right?
Exactly right. The metadata tablets, those other tablets that the root tablet points to, contain the locations of all the user data tablets. Each row in a metadata table essentially stores the location, i.e. the serving tablet server, of a specific user tablet. These rows are indexed by an encoding of the user tablet's table identifier and its end row key.
And these metadata rows, are they big?
No, they're kept very small, typically about 1 kilobyte each. And crucially, the metadata table itself is usually configured to keep its location data in memory, using those in-memory locality groups we'll talk about later, for extremely fast access. This clever 3-level design ensures that even with a truly mind-boggling number of potential user tablets, the paper calculates they could theoretically address up to 234 tablets, representing 261 bytes or about 2 exabytes of data. Bigtable can quickly locate any piece of data with very few network hops.
2 exabytes. That's an absolutely astonishing amount of data to manage with just a 3-level index. So what about efficiency? Does the client library have to traverse this entire 3-level hierarchy every single time it needs to find a tablet's location? Or is there a shortcut? That sounds like it could add latency.
Thankfully, there's a massive shortcut built into the client library. It's actually incredibly smart about caching. It aggressively caches tablet locations it learns about to avoid constantly traversing this hierarchy for every single read or write.
Okay, so it remembers where tablets are. What happens if the location is wrong? Maybe because a tablet moved or split.
If the client doesn't know a location, or if its cache information turns out to be stale, it then recursively moves up the hierarchy to find the correct current path. So a cold cache lookup, meaning the very first time it ever needs to find a particular tablet's location, might take about 3 network round trips. 1 to read the root location from Chubby, 1 to read the relevant metadata tablet location from the root tablet, and 1 to read the user tablet location from that metadata tablet.
And if the cache is just stale?
A stale cache lookup might take a bit longer, maybe up to 6 round trips in the worst case, if it has to invalidate its cache at multiple levels and retry the lookups.
6 round trips still sounds like potentially noticeable latency, especially if the cache isn't hit frequently for some reason. Is there yet another optimization to make this even faster in practice?
There is, and it's an important one: prefetching. The client library is proactive. When it needs to read metadata for one tablet's location, it doesn't just read that single piece of information. It intelligently reads the metadata for multiple tablets nearby in the metadata table at the same time, anticipating future needs, especially during scans.
So it grabs locations for tablets it thinks it might need soon.
Exactly. This significantly reduces the total number of round trips needed for sequential operations like scans, making location lookups much more efficient in practice than those worst-case numbers might suggest. They also store secondary information in the metadata table, like a log of significant events per tablet, like splits or moves, which is incredibly helpful for debugging and performance analysis. It's like checking the table of contents for the entire chapter, not just looking up one page number to save yourself time later when you inevitably need to jump to other sections nearby.
That's a truly clever optimization. It really shows how much thought went into tuning every single layer of this system for performance. We've talked quite a bit about how tablets are stored and located, but in a massive distributed system like this, things inevitably fail. Machines crash, networks get flaky, partitions happen. How does Bigtable ensure high availability, especially when it comes to assigning these tablets to servers and recovering quickly from those inevitable failures?
Yeah, this is where the master's role as the orchestrator becomes absolutely critical. The master is constantly monitoring and managing the overall state of the cluster, maintaining a really vigilant watch over everything.
What's it tracking specifically?
It keeps track of all the live tablet servers, which it knows about because each live server maintains an exclusive lock file in Chubby. And crucially, it also tracks which tablets are currently unassigned.
Unassigned. Why would a tablet be unassigned?
Well, maybe because the server that was previously hosting it just died, or perhaps a new tablet was just created through a split and hasn't been assigned yet. When a tablet becomes unassigned and the master sees there's a healthy tablet server with enough capacity, the master assigns the tablet to that server by sending it a specific tablet load request message.
Okay, so how precisely does the master detect when a tablet server goes down or becomes unresponsive? Does it just ping them constantly?
It relies heavily on Chubby for this fault detection mechanism. It's pretty clever. When a tablet server starts up, it acquires an exclusive lock on a uniquely named file within a specific directory in Chubby. The master monitors this directory to discover new tablet servers joining the cluster.
Okay.
Now, if a tablet server loses its exclusive lock, maybe because a network partition cuts it off completely from the Chubby service, it immediately stops serving requests for all its tablets. This is a crucial self-preservation mechanism to prevent inconsistent state.
So it takes itself offline if it can't talk to Chubby.
Right. Meanwhile, the master periodically asks each tablet server for the status of its lock. If a server reports that it lost its lock, or if the master simply can't reach a server for several consecutive attempts, the master then tries to acquire that potentially dead server's Chubby lock itself.
If the master can grab the lock, the original server must have lost it.
Exactly. If the master succeeds in acquiring the lock, it knows for sure that the tablet server is either truly dead or irrecoverably disconnected from the coordination service. At that point, the master deletes the server's lock file in Chubby and marks all the tablets that were assigned to that server as unassigned, making them eligible for rapid reassignment to other healthy servers in the cluster.
That sounds pretty robust for tablet server failures. But what happens if the master itself fails? That seems like a potential single point of failure that could bring the whole orchestration to a grinding halt.
It is a potential issue, but they engineered a good failsafe for it. If the master's own Chubby session expires, meaning it's lost its connection to Chubby, perhaps due to network issues or its own machine problems, the master process deliberately kills itself.
Kills itself. Wow, that sounds extreme. Why?
It sounds extreme, but it's actually a crucial safety measure. It prevents a potentially disconnected or confused master from making bad decisions based on stale or possibly incorrect information about the cluster's state.
Okay. Better safe than sorry. So what happens then? Does the cluster just stop working?
No, don't worry. The overarching cluster management system that runs Google's jobs quickly detects the master's demise and automatically starts a new master process on another machine. And crucially, master failures do not immediately change any existing tablet assignments.
Oh, yes, it's important.
Yeah, the tablets continue to be served by the tablet servers they were already assigned to. A master failure only affects the system's ability to orchestrate new assignments or handle new server failures or schema changes until the new master comes online. So, data serving continues largely uninterrupted, minimizing disruption for users.
That's a really clever way to ensure consistency and enable rapid recovery. How does a newly started master get up to speed so quickly? He needs to figure out the entire state of this potentially huge, sprawling system, right?
It does, and it goes through a very precise 4-step startup process designed to rapidly reconstruct the current cluster state.
Okay, step one.
First, the new master process grabs a unique master lock in Chubby. This ensures that no other process attempts to become the master concurrently, only one conductor at a time.
Step two.
Second, it scans the special servers directory in Chubby to discover all the currently live tablet servers, the ones that have successfully acquired and are still holding their own Chubby locks.
Step three.
Third, it communicates directly with every single one of those discovered live tablet servers to find out which tablets they are already assigned to and actively serving.
Oh, finally.
And fourth, the master performs a comprehensive scan of the metadata table, starting from the root tablet to learn the complete set of all tablets that exist within the entire Bigtable system. If it encounters any tablet during the scan that isn't already assigned to one of the live servers it found in step 3, it adds that tablet to its internal pool of unassigned tablets, making it eligible for assignment later on.
Okay, but wait. How does it kickstart that metadata table scan in step 4 if the metadata tablets themselves need to be assigned first before they can be scanned? That sounds like a classic chicken and egg problem.
Ah, good catch. There's special handling just for the root tablet to break that potential cycle. Before starting the full metadata scan, if the root tablet wasn't discovered as already assigned to a live server back in step 3, the master explicitly adds the root tablet itself to the set of unassigned tablets.
So make sure the root gets assigned first.
Exactly. This ensures the root tablet gets assigned very quickly. Once the root tablet is assigned and the master can scan it, the master then knows the locations of all the other metadata tablets. That allows it to complete the full scan and eventually discover the locations of all the user data tablets. It's a really neat solution to that bootstrapping problem, showing the meticulous detail in their fault tolerance design.
Definitely. What about tablet splits? When a tablet gets too big, are they handled by the master too, or do the individual tablet servers manage that process?
Tablet splits are actually unique because they are initiated by a tablet server, not the master.
Oh, interesting. Why?
Well, the tablet server is the one that knows exactly how big its tablets are getting. So when a tablet grows too large, say beyond its configured size limit, maybe 200 millibeats, by default, the tablet server proactively splits it locally into 2 smaller, more manageable tablets, for example, dividing the row range. It then records this new tablet information, the 2 new tablets replacing the old one, in the metadata table.
And then tells the master.
Right. Once the split information is committed to the metadata table, the tablet server notifies the master about the split. Now, if that notification happens to get lost, maybe the server crashes right after the split or the master fails before processing the notification, it's okay. The master will eventually detect the new, smaller tablets the next time it tries to ask a server to load the original, now split tablet. The server holding the pieces will tell the master about the split it knows about from the metadata table, and the master will update its own records accordingly.
And all this happens without blocking reads and writes.
Correct. The split operation itself and the subsequent notification and discovery process all happen seamlessly in the background without blocking ongoing read and write operations to the data being split, though operations might be briefly paused or rerouted during the final handoff. This is absolutely crucial for maintaining continuous availability and performance as the system scales and adapts.
It really is a sophisticated dance, isn't it? Between the master, the tablet servers, and Chubby, all working together to keep everything running, resilient, and constantly adapting to change and failure. Okay, so we've covered the overall structure and how Bigtable manages its distributed components and handles failures. Now let's get really into the nitty-gritty. How does data actually flow when you read or write something? And how does Bigtable keep all that data organized and efficient over time, especially with something as dynamic as, say, web pages constantly changing or user data being updated?
Yeah, excellent question, because this is where a lot of the performance magic happens right under the hood. So the persistent state of any given tablet in Bigtable is ultimately stored as SS tables on GFS. We know that. Right.
Now, when an update like a write operation arrives at the correct tablet server for a particular row, it first gets checked for authorization. Does this client have permission? And also whether it's well-formed. Does it match the schema rules?
Makes sense. Standard checks.
Then, and this is absolutely critical for durability, the update is immediately written to a commit log. This log stores redo records for the update. It's essential because it ensures that even if that tablet server crashes unexpectedly right after acknowledging the write, but before persisting it elsewhere, no committed writes are ever lost upon recovery.
Okay, the commit log guarantees durability. Is writing to it fast enough?
They use a technique called group commit here, which basically means batching together many small independent write operations destined for the log into larger single writes to GFS. This drastically improves the overall throughput by reducing the number of individual, potentially slow, disk, or network operations needed.
Smart batching. Okay, so all updates hit the commit log first for safety. What happens right after that? Where's the data go next so it can be read immediately? Right. After being safely committed to the log, the updates are then inserted into an in-memory sorted buffer called a mem table.
Mem table. In memory sorted.
Okay,
Okay.
exactly. This mem table holds all the recently committed updates for that specific tablet. Because it's in memory and sorted, it provides very fast, low latency access for reads that need the absolute freshest data. Think of it as a rapidly updating, write-optimized cache that sits in front of the persistent storage.
And the older data, the stuff not in the mem table.
Older updates, the ones that have already been persisted from previous mem tables and maybe compacted, are stored in that sequence of immutable SS tables on GFS that we talked about earlier.
Okay, so when a read operation comes in for a particular row and column, how does the tablet server find the right value, given that the data could be in the transient in-memory mem table or spread across potentially many different immutable SS tables on disk?
Great question. When a read operation arrives and passes the auth checks, the tablet server doesn't just look in one place. It intelligently constructs a merged view of the data on the fly.
A merged view.
This merged view combines the contents of the current in-memory mem table, which has the absolute latest writes, and all the relevant on-disk SS tables for that tablet. Because both the mem table and all the SS tables are individually sorted by row key, column key, and timestamp, this merge can be performed very efficiently.
Oh, like merging multiple sorted lists.
Exactly. It's like having several perfectly sorted lists of names and needing to find a specific name across all of them. You can do it really quickly by comparing elements from the head of each list simultaneously without having to scan every single item in every list. This multi-source merge-on-read strategy is key to providing consistent read performance even as data gets updated.
Okay, that explains reads and writes. But you mentioned earlier that web pages change, users update profiles, versions are kept. How does Bigtable handle all these updates and deletions over time to keep things from getting totally out of control, with multiple versions piling up or logically deleted data still taking up precious disk space? This sounds like where those compactions you hinted at come in, almost like a background cleanup crew.
Compactions are indeed the unsung heroes, the tireless janitors of data within Bigtable. They're absolutely critical for maintaining efficiency, performance, and controlling disk usage over the long term. They quietly work away in the background, making sure everything stays tidy and performant.
Okay, let's break them down. The paper mentions a few types. What's a minor compaction?
So as write operations keep executing, that in-memory mem table continuously grows. When it reaches a certain size threshold, which is configurable, the tablet server freezes. It essentially stops accepting new writes into that mem table.
Yeah.
At that exact moment, a new empty mem table is immediately created to take over, handling all the incoming writes, ensuring there's absolutely no interruption to the write service. The now frozen mem table is then converted into a brand new SS stable file and written out persistently to GFS. This whole process is called a minor compaction.
And why do this? What are the goals?
It has two main goals. First, it shrinks the memory usage of the tablet server because the data is moved from RAM to disk via GFS, which is crucial for stability. Second, it reduces the amount of data that would need to be read back from the commit log during recovery if that server happened to crash. Less data in the mem table means faster recovery. And crucially, incoming read and write operations continue completely uninterrupted while these minor compactions happen in the background. They're designed to be totally non-blocking.
Okay, so minor compactions turn mem tables into SS tables. But if every minor compaction creates a new SS stable file on GFS, wouldn't you eventually end up with just hundreds or thousands of tiny SS tables that a read operation would have to check every single time? That sounds like it would eventually slow reads right down.
You absolutely would, and that's precisely why they also have merging compactions. Periodically, the Bigtable tablet server executes a merging compaction process in the background.
What does that do?
This process reads the contents of a few existing SS tables, maybe some smaller ones created by recent minor compactions, and potentially the current mem table as well, merges all their sorted data together into a single consolidated sorted stream, and then writes out a new, larger, combined SS table.
Combining files.
Exactly. The old import SS tables and potentially the mem table that were just merged can then be safely discarded and their space in GFS reclaimed. This merging process intelligently limits the total number of distinct SS tables that any given RAID operation needs to consult, which directly improves read performance by reducing the number of files to check. It's like periodically merging a whole bunch of small, sorted piles of papers into one bigger, neatly sorted pile. Makes finding things much easier.
That makes sense. And then there's the major compaction, which sounds like the really big, deep, clean operation. What's its purpose?
Indeed, a major compaction is the ultimate cleanup operation for a tablet. It takes all the existing SS tables for a given tablet, reads every single key value pair from all of them, and rewrites them into one single, new, consolidated S table.
Why rewrite everything? Isn't that expensive?
It is more resource intensive, which is why it happens less frequently than minor or merging compactions. But it's vital for two main reasons. First, it's the primary mechanism for reclaiming disk space that was being used by data that has been logically deleted or superseded by newer versions. Remember, when you delete data in Bigtable, it's often just marked for deletion with a special tombstone marker or simply overwritten by a newer timestamped version in the mem table or a newer SS table. Major compactions are what actually remove that deleted or old data permanently from the persistent storage, ensuring it truly vanishes from the system in a timely fashion. This is paramount for managing storage costs and also for handling sensitive information or meeting compliance requirements where data needs to be verifiably deleted.
Okay, space reclamation is key.
Yeah.
Any other benefit?
Yes. The second benefit is that after a major compaction, reads for that tablet only ever need to consult one SS table, plus the current mem table, which can further improve read performance in some cases. And again, just like the other compaction types, major compactions happen continuously and transparently in the background, designed to minimize impact on ongoing read and write operations, ensuring Bigtable remains responsive and efficient even while housekeeping.
It's really fascinating how they manage the inherent mutability of real-world data updates, deletions, versions within an architecture that's primarily built on these largely immutable SS-stable files. This clever interplay between the mem table, the commit log, and these different background compaction strategies seems absolutely fundamental to Bigtable's efficiency and scalability. Okay, it's one thing to design a brilliant system like this on paper, maybe even build a prototype, but it's quite another to see it deployed successfully at Google's immense scale and have it actually power critical applications. What were some of the key performance enhancements and meticulous refinements that the Google engineers layered on top of Bigtable's core design to really squeeze out every last drop of speed and efficiency in the real world?
Oh, they were truly relentless in their pursuit of optimization. It wasn't enough to just work. It had to work incredibly fast and efficiently. One really key enhancement they introduced is the concept of locality groups.
Locality groups? What are those?
Clients can choose to group multiple column families together into what's called a locality group. Bigtable then intelligently generates and stores a separate SS stable file on GFS for each distinct locality group within a single tablet.
Okay. Why is separating column families to different files beneficial? What does that actually achieve in terms of real-world performance?
This is actually incredibly powerful for performance tuning. Imagine, again, our web page example stored in Bigtable. You might have one column family, maybe called metadata, that stores small, frequently accessed information like the page's language, its checksum, maybe the last crawl time, small stuff.
Right.
And then you have another column family, say contents, that stores the massive multi-megabyte actual HTML content of the page, which you might access much less frequently. By putting these two column families into separate locality groups, if an application only needs to fetch the metadata, which happens a lot, maybe just to check if the page changed, it only needs to read the small SS stable associated with the metadata locality group. It doesn't have to read through or even touch the potentially huge SS stable containing the page content itself.
Ah, I see. It avoids reading unnecessary data from disk.
Exactly. This saves massive amounts of disk I/O and network bandwidth, especially for reads that only need a small subset of a row's columns. You only read the data blocks you truly need. It's like having separate, highly optimized drawers for different types of information in your filing cabinet. You don't have to rummage through everything to find one small item.
That makes a lot of sense. And the paper mentions some locality groups can even be declared in memory. What's the impact of doing that on speed?
Right. For data that's relatively small but needs to be accessed extremely frequently with the lowest possible latency, clients can declare a locality group as being in memory. This tells the tablet server to try and keep the SS tables for these specific groups loaded lazily into its main memory.
So reads hit RAM instead of disk.
Exactly. Reads for data in these in-memory locality groups can often be served entirely from the tablet server's RAM, completely avoiding any disk access, which makes them incredibly fast. The metadata table itself, which stores all the tablet locations, uses this feature for its crucial location column family. That's a big part of why Bigtable's internal location lookup process is so unbelievably fast.
Wow. Okay. So tuning locality groups seems really important. Beyond data layout, what about data compression? That must be absolutely crucial when you're talking about storing petabytes of data efficiently.
Oh, absolutely critical. And again, Bigtable gives clients fine-grained control. They can decide on a per locality group basis whether to compress the SS tables stored on GFS and even which specific compression format to use.
Does Bigtable offer special compression algorithms?
Yes, it leverages a clever, custom two-pass compression scheme that was designed specifically for speed and effectiveness on the types of data Google often stored. The first pass employs a variant of the Bentley and McElroy scheme, which is particularly good at finding and compressing long, common strings across a large window of data, think shared HTML boilerplate or common prefixes.
Okay. And the second pass?
The second pass uses a different, very fast compression algorithm that's good at finding smaller, repeating byte sequences within a smaller window. Both passes are designed for incredible speed. The paper mentions encoding data at 100, 200 millibsecond and decoding even faster at 400, 1000 millisecond on the machines back then. This ensures that compression itself never becomes a performance bottleneck for reads or writes, which is absolutely essential when you're dealing with Google's web-scale data volumes and traffic.
That sounds impressively fast.
Yeah.
But how effective is this custom scheme compared to, say, a standard well-known compression algorithm like gzip? Does it actually save more space?
Surprisingly, in many common cases, it's far more effective. For the web table example, storing web page contents, this custom two-pass scheme achieved an astonishing 10-to-1 reduction in space on average.
10 to 1.
Yeah. Compare that to gzip's typical 3-to-1 or maybe 4-to-1 compression ratio for HTML files.
Why is it so much better?
The reason for this phenomenal performance ties back directly to that smart row key design we discussed earlier, reversing the host name. Because all the pages from a single host are stored lexicographically close together, often within the same S-stable blocks.
Ah, the compression algorithm sees similar data together.
Exactly. This allows the compression algorithm, especially that first pass looking for long common strings, to identify vast amounts of shared boilerplate text, like common headers, footers, navigation menus, across many pages from the same domain. It finds way more redundancy than gzip typically would, compressing individual files separately. It really highlights the powerful symbiotic relationship between smart data modeling, how you design your keys, and physical storage efficiency.
That's a really powerful testament to the idea that how you organize your data impacts literally everything downstream, even down to the raw storage efficiency. Okay, what about more general caching techniques just for speeding up read performance?
To further boost read performance, especially for data that isn't declared in memory, tablet servers employ two distinct levels of caching.
Okay, 2 levels, what are they?
The first is the scan cache. This is a higher level cache that stores the specific key value pairs returned by the SS stable interface to the client. It's particularly effective for applications that tend to repeatedly read the exact same data over and over.
Okay, caches results, what's the other level?
Below that is the block cache. This is a lower level cache that stores raw blocks of data. Remember, as stables are made of blocks, maybe 64 KCB each, that have been read from GFS. This cache is useful for applications that exhibit good temporal or spatial locality, meaning they tend to read the same data block multiple times, or they read data that is physically close within an SS stable block to data they recently accessed, like during a range scan.
Got it. 2 layers of caching for reads. Now, I've heard about Bloom filters being almost magical for speeding up lookups, especially for checking if something doesn't exist. How does Bigtable use those?
Yeah, Bloom filters are indeed almost magical in their efficiency for this kind of task. Remember, a read operation might need to check multiple SS stable files on disk to find the requested data for a specific row and column. If these SS stables aren't entirely in memory, in the block cache, checking each one could mean performing several slow disk accesses.
Right. Disk seeks are expensive.
Exactly. Bloom filters offer a very clever way to avoid many of those unnecessary disk reads. There are small, probabilistic data structures stored in memory that can very quickly tell you if an SS stable might contain data for a specific row-column pair you're looking for. The key is, if the Bloom filter definitively says no, you know with 100% certainty that the data is not in that SS stable, so you don't even bother trying to read it from disk.
It avoids looking in files that definitely don't have the data.
Precisely. This drastically reduces the number of unnecessary disk seeks, especially for lookups of data that doesn't actually exist in the table, which can be surprisingly common. It makes read operations much, much faster on average, particularly for sparse data sets.
That's a huge saving on I/O. Very clever. Okay, let's switch gears slightly to writes. What about the commit log? You mentioned group commit for efficiency earlier. How did they refine the commit log implementation itself to handle the immense write throughput Google needed?
This is another area with some really smart optimization. The initial, perhaps naive thought might be to have a separate commit log file on GFS for each tablet.
Seems logical, isolates tablets.
It does, but that would lead to potentially thousands of log files being written to concurrently on a single tablet server. This would likely overwhelm GFS with many small writes and drastically reduce the effectiveness of that group commit batching technique we talked about.
Too many small writes again.
Right. So the brilliant solution they implemented was to use a single commit log file per tablet server. This single log commingles mutations, writes and deletes, from all the different tablets being managed by that server into the same physical log file on GFS.
One log file for potentially hundreds of tablets.
Exactly. This is a massive optimization for write throughput because it maximizes the opportunity for batching writes together into larger, more efficient chunks before sending them to GFS.
Okay, that speeds up writes. But wait, commingling all those updates sounds like it could really complicate recovery if a tablet server dies. Mutations for many different tablets would be completely interleaved in that single log file. How do they sort that mess out when tablets get reassigned?
You're absolutely right, it does complicate recovery. If a tablet server managing, say, 100 tablets crashes, those 100 tablets might get reassigned to maybe 50 different other healthy tablet servers. Each of those 50 new servers now needs to replay only the relevant mutations for the specific tablets it just inherited, reading them from that single massive interleaved commit log file left behind by the dead server.
That sounds inefficient. Does each server have to read the whole log?
No, that would be way too slow. Instead, they have a clever recovery coordination process. When a master tells a server it needs to recover a tablet using a specific commit log, the recovery process doesn't just read the log sequentially. First, they sort the commit log entries. The sorting key is a tuple: table name, row name, log sequence number.
Sorting groups all entries for the same tablet together.
Precisely. This sorting step makes all the mutations for any specific tablet contiguous within the sorted output. Now, each recovering tablet server can perform efficient sequential reads to get just the mutations needed for the specific tablets it's responsible for without having to scan the entire log file.
That's smart. But sorting a potentially huge log file sounds slow too.
It could be, so they parallelize the sorting process itself. They partition the original commit log file into large-ish segments, for example, 64 MB, and the master assigns different tablet servers to sort different segments in parallel. This dramatically speeds up the overall recovery process.
Wow, okay. Parallel recovery sorting. And they even built in resilience to GFS latency spikes specifically for writing to the commit log. How do they do that?
Yes, another subtle but really important refinement for consistent high throughput. Each tablet server actually maintains 2 log writing threads, each writing to its own separate log file in GFS. However, only one thread and its corresponding file is considered active at any given time.
Why two?
If the currently active log writing thread starts experiencing poor performance, maybe because the specific GFS server it's writing to is slow or experiencing latency spikes, the tablet server proactively switches its logging activity over to the other thread and its log file. This ensures that temporary GFS hiccups don't stall the critical commit logging process. They use sequence numbers within the log entries to handle potential duplicate entries during recovery that might arise from this switching.
That's incredibly robust, thinking about every possible bottleneck. And finally, what about speeding up tablet recovery when they intentionally move tablets between servers, say for load balancing, not just when a server crashes unexpectedly?
Good question. They optimize that transition too. When the master decides to move a tablet from server A to server B, maybe because server A is overloaded, server A performs a minor compaction on that specific tablet before unloading it.
Why compact before moving?
This reduces the amount of uncompacted state in the tablet's mem table that would otherwise need to be replayed from server A's commit log by server B during the recovery loading process. After that first minor compaction finishes, server A does another, usually very fast minor compaction to flush any tiny amount of data that might have arrived just during the first compaction. This ensures that the new tablet server, server B, can load the tablet with almost zero state needing recovery from server A's commit log, significantly speeding up the transfer and making the tablet available much faster on its new host.
It's fascinating how much of this incredible efficiency, from reads to writes to compactions to recovery, seems to stem from one really fundamental design principle, the immutability of those SS tables.
You've absolutely hit on the philosophical core of much of Bigtable's efficiency and simplicity, Alex. The fact that all those S-tables, once written to disk via GFS, are never changed, they're immutable, simplifies so many aspects of this incredibly complex distributed system.
How so? Give me some examples.
Okay, well, for one, since SS tables never change, no synchronization or locking is needed for reads accessing them. Multiple reads can hit the same SS table concurrently without interfering with each other. This makes concurrency control much simpler and more efficient. The only truly mutable data structure is the relatively small in-memory mem table, and even there, they use clever techniques like copy-on-write internally to reduce contention and ensure consistency during reads and writes.
Okay, simplified concurrency. What else?
Deleting data becomes much simpler, too. It's essentially just a garbage collection problem. You mark data as deleted or write a newer version, and eventually the old SS tables containing the deleted data become obsolete and are simply garbage collected by the master during compaction cleanup. You don't have complex in-place updates or fragmentation issues common in mutable storage systems.
And tablet splits, you mentioned those earlier.
Immutability makes tablet splits incredibly fast and efficient. When a tablet splits into two children, the child tablets don't need to copy all the data. They simply share the same underlying immutable SS tables inherited from their parent tablet. They just operate on different row ranges within their shared files. Only new data written after the split goes into new, separate SS tables for each child. This avoids massive, slow data copying during splits. Immutability truly underpins so much of Bigtable's robustness, its relative simplicity despite its scale, and its blazing speed.
It's really amazing how adhering to a simple design principle like immutability can cascade into so many tangible benefits across such a complex distributed system.
A real lesson there. Okay, so we've established Bigtable was a brilliant system design on paper, packed with clever optimizations. But the real proof is in the pudding, right? What was its actual real-world impact? How extensively was it actually applied within Google by the time this paper was written in 2006? Was it just experimental, or was it core?
Oh, it was absolutely core. By August 2006, which was just over a year after its initial production launch in April 2005, Bigtable was already underpinning a significant and rapidly growing portion of Google's entire operations. This wasn't some side project or experimental prototype. It was mission-critical infrastructure.
How big was the deployment back then?
The paper reports there were 388 non-test Bigtable clusters running across various Google machine clusters worldwide, and those clusters comprised a combined total of approximately 24,500 tablet servers. 24,500 tablet servers. Wow.
Oh.
That's like having a small city's worth of dedicated database machines just for Bigtable back in 2006.
It was a truly massive, absolutely mission-critical deployment, yeah.
And what kind of traffic were these clusters handling? Were they just sitting there storing data, or were they actively serving requests?
They were incredibly active. They reported data from one group of 14 particularly busy clusters, which involved over 8,000 tablet servers just in that group. Collectively, those 14 clusters were handling more than 1.2 million requests per second.
1.2 million per second.
And the data flow was immense, too. The incoming RPC traffic to these clusters was around 741 megabytes per second, and the outgoing RPC traffic data being read out was even more impressive, hitting about 16 gigabytes per second.
16 gigabytes a second.
Yeah. So this clearly isn't just about static storage. It demonstrates Bigtable's capability to serve and process absolutely immense data streams at real-time speeds for Google's live, user-facing applications. It was like a fire hose of data constantly flowing in and out.
Okay, let's dive into some specific examples mentioned in the paper.
Yeah.
How did a service like, say, Google Analytics leverage Bigtable back then?
Right. Google Analytics, which helps website owners analyze their traffic patterns and user behavior. It used Bigtable for two main types of tables. First, they had a huge raw click table. This stored details about every user interaction, and it was around 200 terabytes in size at the time.
200 terabytes of clicks.
Yeah.
How was that structured?
It maintained a row for each unique end-user session, and the row name itself was a cleverly constructed tuple containing the website's name and the session creation time. This design ensured that all sessions from the same website were stored contiguously in the table and were also chronologically sorted, which made generating reports for specific websites much more efficient. And interestingly, this raw click table compressed remarkably well using Bigtable's compression, shrinking down to just 14% of its original raw size.
Wow, 14%. That's huge savings. And then they would aggregate that raw data into summaries, I imagine, for faster reporting.
Exactly. They also had a summary table, which was much smaller, around 20 terabytes. This table contained pre-calculated, predefined summaries for each website, things like total page views, unique visitors per day, etc. This summary table was generated periodically from the raw click data using MapReduce jobs that read from and wrote back to Bigtable.
And was this summary table faster to access?
Yes, it was much more latency sensitive than the raw click table because it directly powered the real-time dashboards that website owners would look at. It still compressed reasonably well, down to about 29% of its original size. This whole setup really showcases Bigtable's versatility, handling both massive raw data sets, primarily for batch processing, and smaller, aggregated, performance-critical data needed for real-time serving, all within the same system.
Okay, what about something visually intensive like Google Earth with all its vast satellite imagery? How did Bigtable fit into that picture?
Google Earth also used Bigtable in a really interesting dual capacity, again highlighting its ability to handle hybrid workloads. For the back-end pre-processing of raw satellite imagery, they had one Bigtable table storing about 70 terabytes of data. This table was primarily disk-served, not in memory, and they didn't even use Bigtable's internal compression for this table, because the images themselves were already efficiently compressed in their native formats like JPEG.
And how was that table organized?
The rows were named in a way that ensured adjacent geographic segments were stored close together, again for locality. And it had a sparse column family used for tracking data sources, with basically one column qualifier for each distinct ROG image that contributed to that map tile. This whole pre-processing pipeline relied heavily on MapReduce jobs running over Bigtable, crunching through that image data at over 1 millibits per second per tablet server.
Okay, so that's the back-end number crunching to prepare the maps. What about serving the actual maps and index data to users, enabling that smooth, low-latency zooming experience we all know?
Right. The sorting system for Google Earth used a separate, much smaller Bigtable table, only around 500 gigabytes at the time. This table primarily served as an index to the actual image data, which is likely stored directly in GFS. This index table had incredibly demanding performance requirements. It had to serve tens of thousands of queries per second per data center with very, very low latency.
How did they achieve that speed?
To achieve that kind of performance, this serving table was hosted across hundreds of tablet servers, and it heavily utilized those in-memory locality groups we talked about earlier for its critical index data. This is a fantastic real-world example of Bigtable supporting both massive, throughput-oriented batch processing on the back end and simultaneous real-time, ultra-low latency serving on the front ends, all using the same core storage technology.
That's really impressive versatility. Okay, one more example. Personalized search. That sounds like a very personal, user-centric application where data privacy, speed, and maybe flexibility in storing different types of user actions would be paramount. How did they use Bigtable there?
Right, personalized search, which aimed to tailor Google search results based on your past activity. It stored each user's data in Bigtable, using the unique user ID as the row key.
Makes sense. One row per user.
Exactly. And then different types of user actions like web queries they issued, results they clicked on, maybe image searches they performed were stored in separate column families within that user's row. And the Bigtable timestamp associated with each data element naturally recorded precisely when that user action occurred.
So it automatically built up a timestamped history.
Precisely. User profiles were then generated using MapReduce jobs that read this historical data from Bigtable. And these profiles were subsequently used by the live search system to personalize search results in real time, dynamically adapting to the user's recent behavior captured in Bigtable.
That makes perfect sense for storing and processing individual user data. Did they encounter any unique challenges with personalized search that actually influenced Bigtable's own evolution or led to new features?
Yes, they did mention a couple of interesting points. First, the personalized search data was critical, so it needed to be highly available. It was replicated across several different Bigtable clusters in different data centers to boost availability and also reduce latency for clients accessing it globally. Initially, they built their own client-side replication logic to manage this.
Application-level replication.
Right. But eventually they realized this was a common need and integrated support for server-side replication directly into the Bigtable servers themselves as a core feature, simplifying things for applications.
Okay, built-in replication. What else?
Also, because personalized search stored this rich user data, many other groups within Google wanted to piggyback on it and store their own per-user configuration options and settings in the same shared personalized search tables. This led to what the paper calls an unusually large number of column families being used in those tables, as each group added their own.
Oh, sounds like it could get messy or one group could hog resources.
Exactly. To manage this shared resource effectively, the Bigtable team added a simple quota mechanism. This allowed them to limit the total storage consumption by any single client application within these shared tables, providing some basic isolation and preventing one group from accidentally monopolizing storage resources needed by others. It's a great example of how real-world usage patterns and challenges directly drove necessary new features back into the core Bigtable system.
It really shows how Bigtable truly became this foundational piece for so many of Google's core services, constantly adapting to these varied and incredibly intense demands. It's pretty remarkable to see just how widely and deeply it was adopted so quickly across the company.
Yeah.
Okay, building a system of Bigtable scale and ambition inevitably comes with a lot of lessons learned, often, the hard way through operational experience. What were some of the most significant takeaways for the Google engineering team that they actually shared in the paper? What did they learn from running this beast?
Yeah, they shared some really insightful lessons. One of the most important ones, and honestly one that resonates deeply with anyone who's ever worked on large-scale distributed systems, is that these systems are often far more fragile in practice than you might initially assume based on theory.
More fragile. How so?
Well, they don't just experience the standard kinds of failures that many theoretical distributed protocols focus on, like clean network partitions or simple fail-stop failures where a machine just cleanly dies. Google encountered a whole host of much messier real-world problems.
Like what?
Things like subtle memory corruption or network data corruption that wasn't caught by lower layers, large clock skew between machines causing timing issues, machines that didn't crash but simply hung indefinitely, becoming unresponsive zombies, extended and sometimes asymmetric network partitions where A could talk to B but B couldn't talk back to A, bugs in other foundational systems they were relying on, like discovering issues in Chubby itself, running into GFS quota overflows unexpectedly, and of course dealing with both planned and unplanned hardware maintenance taking machines offline.
Wow, that's a sobering list of really nasty, hard-to-debug problems. How did they adapt to such a wide range of unpredictable failures that go way beyond the typical textbook scenarios?
They really had to adapt by fundamentally changing various protocols and hardening their assumptions about the environment. For instance, they found they had to add checksumming to their own RPC, remote procedure call mechanism, to detect subtle network corruption that could otherwise lead to silent data errors propagating through the system.
So adding their own checks on top.
Right. They also had to explicitly remove assumptions that one part of the system might implicitly make about another part. For example, they stopped assuming that a given Chubby operation could only return a specific, predefined set of errors based on its API documentation. They had to become prepared for anything that Chubby might return in practice, including completely unexpected error codes they'd never seen before, maybe due to bugs or weird edge cases in Chubby itself.
That sounds like defensive programming taken to the extreme.
It really highlights the practical realities that push engineers way beyond theoretical idealizations when building systems at this scale. Debugging those hung indefinitely machines must have been particularly soul-destroying. You can just imagine the frustration.
Slight chuckle.
Okay.
I can only imagine. That's a great lesson for anyone building complex software. Expect the unexpected and then some.
What about feature development? Did they find that just adding every feature requested by users was beneficial? Or was there a more strategic approach they learned?
Actually, quite the opposite. Another really key lesson they emphasized was the profound importance of delaying the implementation of new features until it becomes absolutely clear how those features will actually be used in practice by real applications.
Delaying features. That sounds counterintuitive sometimes. Give me an example.
Okay, the prime example they give is general purpose transactions. They initially planned to support transactions spanning multiple rows in Bigtable's API, similar to what relational databases offer,
Right.
because it sounds like a logical thing for ensuring data consistency.
Yeah, seems standard. But crucially, because there wasn't an immediate pressing use case demanding multi-row transactions from their initial set of internal applications, they didn't actually implement them right away. They put it off.
So they waited and then saw what the real organic needs were from their actual internal users over time.
Exactly. And this pragmatic wait-and-see approach saved them potentially immense development and maintenance effort. Now, with many real applications running on Bigtable for a while, they were able to go back and objectively examine what clients actually needed in terms of transactional guarantees.
And what did they find?
They discovered that the vast majority of applications required only those single-row transactions, the atomic read-modify write guarantee within a single row, which Bigtable already provided efficiently. For the few cases where distributed transactions across multiple rows were being requested, they found it was primarily for maintaining secondary indices on the data, basically, creating alternative ways to look up data based on values in columns, not just the row key.
Ah, okay. A specific use case.
Right. So instead of implementing a full, complex, and potentially inefficient general distributed transaction system that might be overkill, this insight led them to plan a specialized, more optimized mechanism specifically for supporting secondary indices. This specialized mechanism would likely be more efficient and interact better with their plans for cross-data center replication. It's really a masterclass in lean, demand-driven engineering applied to infrastructure.
That really is classic lean development thinking, just applied at a massive global infrastructure scale. Fascinating. What else did they learn was absolutely essential for keeping such a complex living system healthy and understandable over time? Monitoring, perhaps.
Absolutely critical. A very practical, hard-won lesson was the critical importance of proper, deep system-level monitoring. And this didn't just mean monitoring Bigtable servers themselves. It meant monitoring the client processes using Bigtable and monitoring all of its underlying dependencies like GFS and Chubby, too.
How do they implement that?
For instance, they extended their RPC system to optionally keep detailed traces of important actions, like lock acquisitions, GFS reads writes, for a small sample of all RPCs flowing through the system. This sampling approach provided invaluable insight without overwhelming the system.
And what did these traces help them find?
They were invaluable for detecting and fixing really subtle performance problems. Things like unexpected lock contention on internal tablet data structures, periods of slow writes to GFS during Bigtable mutations, or even finding instances where client requests were getting stuck trying to access the metadata table because a metadata tablet had temporarily become unavailable. Things you'd never find otherwise.
Wow, so observability wasn't an afterthought, it was core.
Totally. Every Bigtable cluster was also registered in Chubby, which allowed a central system to easily track the size of all clusters, the software versions they were running, their traffic levels, and quickly spot any clusters experiencing unexpected latency problems. Observability really became their third eye for managing this complexity.
Okay, so deep observability was paramount for keeping such a complex system healthy and performant day to day. Looking back at the whole project, what did the paper say was the most important lesson they learned? The overarching takeaway from the entire experience of building and running Bigtable.
The paper concludes pretty emphatically that the most important lesson learned was the enduring value of simple designs.
Simplicity. Even in a system this complex.
Especially in a system this complex. They note the sheer size of the Bigtable codebase, around 100,000 lines of non-test C++ code, which is substantial. And they emphasize that because code inevitably evolves in unexpected ways over time and is maintained by many different engineers, clarity and simplicity in the code and the underlying design were immensely helpful for ongoing maintenance and especially for debugging. They even shared a really powerful anecdote about their experiences with the tablet server membership protocol, which truly underlines this point about simplicity winning in the long run.
Ooh, tell us about that. I love hearing about engineering wisdom that was clearly gained from some painful real-world experience.
Okay, so their first attempt at a protocol for managing tablet server membership and detecting failures was conceptually simple on the surface. The master would periodically issue time-based leases to tablet servers. If a server's lease expired before it could renew it, maybe due to network issues or master load. The master would assume the server was dead and immediately reassign its tablets.
Seems reasonable. What was the problem?
The problem was, this simple lease-based protocol significantly reduced the system's overall availability in the presence of common real-world network problems or master hiccups. It was overly sensitive to transient issues and how quickly the master could recover and reissue leases. So they redesigned it, multiple times in fact, trying to improve performance and robustness. But the resulting protocol became increasingly complex. It started depending on subtle and often esoteric behaviors of certain Chubby features that weren't frequently used by other applications at Google, and thus maybe weren't as well understood or battle-tested. This led to them encountering all sorts of obscure, hard-to-reproduce corner cases. They found themselves spending, and I quote, an inordinate amount of time debugging obscure corner cases, not just in their own Bigtable code, but sometimes having to dive deep into Chubby's own code base to understand why things weren't behaving as expected under specific failure conditions.
That sounds like an absolute debugging nightmare. Chasing ghosts across multiple, incredibly complex distributed systems. Nobody wants to be doing that.
Precisely. So eventually they took a pretty radical step. They completely scrapped that overly complex homegrown membership protocol. They threw it out. And they moved to a newer, simpler protocol that relied solely on widely used and well-understood Chubby features, like the basic lock acquisition and monitoring mechanisms we discussed earlier.
Wow, scrapped it all and went back to basics.
Yeah. And this is such a powerful anecdote about engineering wisdom, I think. Sometimes the best path to robustness and long-term maintainability isn't adding more complexity or trying to be overly clever with intricate protocols. Sometimes it's about simplifying, even if it means throwing out a lot of previous work that seems smart at the time. Simple designs generally lead to clearer code, fewer hidden bugs, and much easier debugging, especially in these large, evolving distributed systems where the inherent complexity can quickly become overwhelming if you're not careful.
That's a really profound takeaway, especially in a field like computer science that sometimes leans towards more complex, seemingly elegant solutions. Maybe sometimes the most truly elegant solution is simply the most understandable and maintainable one in the long run. Okay, Bigtable was clearly revolutionary for its time. But, it didn't exist in a complete vacuum, of course. How did it relate to other existing work in the database and distributed systems field back then? And what really made its approach truly distinctive? Was it just another database variation, or was it something fundamentally different?
That's a crucial distinction to make, Alex. Bigtable is definitively not a traditional relational database. It's not like the commercial systems that were dominant then, like Oracle, RAC, or DB2 Parallel Edition.
How is it different from those?
Well, those systems provide a full relational data model, tables, rows, columns, strict schemas, foreign keys, and, critically, they offer general-purpose ACD-compliant transactions that can span multiple rows or even multiple tables. Bigtable, on the other hand, offers a completely different, much simpler interface and data model. It doesn't aim to be a general-purpose database supporting complex SQL query languages or needing the overhead of complex query optimization and multi-row transaction management.
Right, it focused on Google's specific needs.
Exactly. It provides a much more streamlined model, intentionally omitting the full relational overhead and general transactions because they simply weren't needed for its primary use cases at Google's massive scale. It was built to solve a different, more specific set of problems really, really well.
Okay, so it's clearly not relational. But is it maybe just a fancy key-value store then? We've seen a ton of distributed key-value stores emerge over the years, especially since this paper came out. Was Bigtable just an early one of those?
While it fundamentally uses key-value pairs at its absolute core mapping, that row, column, time, tuple to a value string, Bigtable's data model is significantly richer and more flexible than the simple distributed hash tables, DHTs, like CAN, CHORD, or Pastry, which were also prominent topics of research around that time.
How is it richer?
Well, those DHTs often addressed a different set of problems, like operating in peer-to-peer networks with potentially untrusted participants, handling very frequent node arrivals and departures, churn, or needing Byzantine fault tolerance. Bigtable, operating entirely within Google's trusted and professional managed data centers, didn't have those specific security constraints or extreme churn requirements. Its unique, sparse, semi-structured data model, with its explicit three-dimensional indexing row, column, and timestamp, plus the client's granular control over data locality via locality groups, provides far more expressiveness and performance tuning capabilities than a basic flat key-value pair store typically offers. The paper calls it a useful building block, but one that's been significantly enhanced and specialized for Google's high-performance, large-scale needs.
Okay, so richer than a basic key value store. What about the concept of column-oriented storage? That sounds somewhat similar conceptually to how Bigtable groups data using column families, locality groups, right? Storing columns together.
You're perceptive to notice that similarity, yes. Bigtable's concept of locality groups, where specific column families are intentionally grouped and stored together physically in separate SS stables on disk, does achieve similar benefits to what traditional column-oriented databases, like CStore, which was another influential paper around that time, or commercial products like Sybase IQ, aim for.
What are those benefits again?
The main benefits are usually better compression ratios because you're storing data of the same type together contiguously, and improved read performance for queries that only need to access a subset of columns because you only read the data for the columns you need from disk.
Okay, so similar benefits. Is Bigtable just a column store then?
Not exactly. While it leverages that column grouping idea for efficiency, Bigtable's overall API, its data model, especially the timestamp dimension and sparse nature, and its primary use cases still differ significantly from those dedicated column stores. CStore, for example, was primarily designed as a read-optimized relational DBMS, heavily focused on analytical queries, OLAP. Bigtable, as we've seen, successfully handles both read-intensive and write-intensive transactional-like applications, OLTP-like, but with single-row atomicity, with extremely high performance. So it uses a similar storage technique, but within a different overall system design and for a broader range of workloads.
Got it. And one more comparison, its underlying storage mechanism, that whole system using the in-memory mem table and the immutable S tables on disk with background compactions merging things together. That really reminds me of another well-known data structure concept.
Indeed, it should. The way Bigtable uses mem tables, which are essentially sorted buffers in memory, and SS stables, which are immutable sorted files on disk to store updates, and then periodically merges them through compactions, is conceptually very analogous to the log-structured merge tree, or LSM tree, which was described in earlier academic research papers.
LSM trees,
Right.
used in many modern databases now.
Exactly. In both Bigtable and LSM trees, incoming writes are buffered and sorted in memory before being efficiently flushed to persistent storage as immutable sorted runs or files. Read operations then have to intelligently merge data from both the current in-memory component and potentially multiple immutable on-disk components. This overall approach is inherently highly efficient for write-heavy workloads because all writes are essentially sequential, appends first to the commit log, then to the mem table, which are then compacted efficiently in the background. It's a proven pattern for high-throughput storage, and Bigtable adapted and implemented it at an incredible scale.
So it really sounds like Bigtable took inspiration from various brilliant concepts floating around in different areas, distributed systems, databases, storage structures, and then combined and adapted them in truly unique ways to solve its own specific extreme-scale problems. It wasn't just a direct copy of any one thing.
Exactly right. It's a fantastic testament to how practical necessity, driven by immense scale, can fuel true engineering innovation. The Google engineers didn't just pick one existing idea off the shelf. They critically evaluated different approaches, picked and chose the right concepts from sometimes disparate research fields, and then ingeniously adapted, synthesized, and refined them to create something entirely new and incredibly effective for their very specific, incredibly demanding environment. It's really a classic example of engineering pragmatism leading to a genuine breakthrough.
So we've taken a really deep dive into Bigtable today, exploring its design, its underpinnings, its impact. Let's try to wrap things up now by maybe recapping its monumental achievements and looking at its lasting legacy. I mean, this paper is from 2006, but its influence feels much more current, doesn't it?
Oh, absolutely. Bigtable has been an undeniable, really resounding success story for Google, and its influence extends far beyond Google now. As we discussed, it was in continuous production use internally since April 2005. By the time the paper was published in August 2006, it was already underpinning more than 60 distinct Google products and services, everything from search indexing to Google Analytics to Google Earth, personalized search, finance, and many more.
60 products in just over a year.
Yeah, the adoption was incredibly rapid, and its internal users across Google apparently loved the high performance, the incredible scalability, and the consistent availability it provided compared to whatever they were using before. Critically, they found they could scale the capacity and throughput of their applications almost linearly, simply by adding more commodity machines to their Bigtable clusters as the resource demands grew over time. This predictable horizontal scalability was an absolute game changer for planning and growth.
And you mentioned its unusual interface earlier. Was that ever a significant barrier for internal users, or did its practical success and performance just overcome any initial unfamiliarity?
The paper is quite candid in acknowledging that the interface lacking SQL, lacking multi-row transactions, could definitely be unusual for new users, especially engineers who are perhaps more accustomed to traditional relational databases with their rich query languages and full transactional support. However, the sheer number of diverse Google products that successfully adopted and relied on Bigtable, and its continued core operation within Google, and now as a cloud service, to this very day, demonstrates pretty conclusively that its pragmatic design works incredibly well in practice for the problems it was intended to solve.
So its focus was its strength.
Exactly. Its tight focus on the specific needs of Google's massive scale, often write-heavy or latency-sensitive applications, rather than trying to be a general-purpose, one-size-fits-all database model, proved to be its greatest strength. It consciously traded some generality and some familiar relational features for extreme efficiency, scalability, and operational simplicity at scale. And that trade-off clearly paid off enormously for Google.
And what were they looking at for the future of Bigtable, even back in 2006? Does the paper give any hints about where this technology, or maybe even cloud computing in general, was headed?
It does give a few interesting hints. At that time, they mentioned they were already actively working on several significant additional Bigtable features. This included adding direct support for secondary indices, which we discussed, building infrastructure for creating cross-data center replicated Bigtables with multiple master replicas for even higher availability and disaster recovery, and, very significantly, working on deploying Bigtable as a managed service to product groups within Google.
Bigtable as a service,
Right.
internally first.
Right. So individual teams wouldn't need to set up, configure, and maintain their own complex Bigtable clusters anymore. They could just use a centrally managed, reliable service provided by the core Bigtable team. This vision building powerful internal infrastructure services and then making them easily available across the entire company is a clear precursor to how modern public cloud database services like Amazon DynamoDB or indeed Google's own cloud Bigtable service today, would eventually operate years later. They were literally writing the internal playbook for what was to become a dominant model in cloud computing.
Okay, let's really unpack this then as a final thought. What does Bigtable, this paper from 2006, teach us about building massive scale systems today, especially in an era where managed cloud services are the default for so many? Perhaps the most enduring lesson is the immense, maybe even unfair advantage that can come from building custom-tailored solutions when you're operating at the absolute extreme edge of scale and have very specific problems.
That seems right. The control it gave them was key.
Exactly. When you operate at Google's level, controlling your own infrastructure end-to-end, from the file system like GFS to the locking service like Chubby, right up to the database layer like Bigtable, it allows for an unparalleled ability to identify and remove bottlenecks, co-design interfaces, and innovate in ways that using off-the-shelf black box solutions simply might not allow.
Yeah, that deep integration is powerful.
So this raises a really important, maybe even provocative question for all of us developing systems today. In an era dominated by managed cloud services and powerful database as a service offerings, how much control should companies really cede over their foundational infrastructure, especially if they have unique scale or performance needs? And what potentially game-changing competitive advantages might still lie hidden in selectively building your own core technology for your most critical problems, just like Google did with Bigtable, if you truly want to push the boundaries of performance, efficiency, and ultimately what's possible?
That's definitely something worth thinking about.
Something for all of you to mull over as you click around the internet this week, powered by systems that likely owe a quiet debt to Bigtable.
A fascinating and really relevant thought to leave on. Those trade-offs between building custom solutions versus using managed services are just as pertinent today, maybe even more so, than they were back when Bigtable was created.
Indeed they are. And that's our deep dive into Bigtable for today.